Professor Bharat from Kansas State University. Professor Bharat Ratra is a senior cosmologist. He has been in the field for a long time. He did his PhD from Stanford in the mid-80s, followed by postdocs with Colloquium institutes, including SLAC at Stanford, Houston University, Caltech, MIT, and after which he joined Kansas State University in the mid-90s. With that since, and currently he is a distinguished professor there. So Professor Ratra has worked on various aspects of cosmology, the early universe, academic issues. In the late 80s, along with Jim Peebles, he wrote a couple of very influential papers on the role of the scalar field in cosmology. This was revived later in the 90s by Paul Suluman and others of the essence of dark energy. This has become a staple of cosmological models today. In addition, Professor Ratra has worked on various aspects of inflation and connecting observations in cosmology with the theoretical models. So we are very happy to have him here. Unfortunately, it's a short visit. He's only here for today. And he'll tell us today about his take on the current status of cosmology.
Thank you for the very kind introduction. Yes, okay. So thank you. Thank you for a very kind introduction. It's a great pleasure to be back here again. And before I start my talk, I just want to point out this website. It's really nice. It's got some really nice videos about global warming and really clear explanations. And it's useful for people to look at it. So I'm doing cosmology, and it's a really great time to be doing cosmology. I mean, everybody knows that. You can just see that with all the data from telescopes that are coming in. And they're reinforcing two extremely striking results. One, that we don't know 95% of the current energy budget of the universe. The 5% we know are the atoms and molecules of the few charged particles. The other result that's probably going to end up being more profound if it holds up is that the quantum mechanics or relativity of both are incomplete and need to be improved upon. And if that happens, it's going to be pretty revolutionary because quantum mechanics and relativity have been the foundations of physics for over a century. So let me just start with the budget now, the energy budget now that's driving the expansion. We know, so I have a longer introduction. I'm going to go over it a little bit faster and then get to the new stuff in a bit. But this is just for those who aren't familiar. I mean, if everybody's familiar with cosmology here, I can go much, much faster. Can you put up your hands if you're completely familiar with cosmology? Okay, so there's a few people who aren't, so I'll just go over this. So we know that 5% of the energy budget is made up of atoms, and this number started getting pinned down with the discovery of the microwave background in the 60s. And interpreting that as the leftover photons from nucleosynthesis. That was looked at by Gamow and his graduate student and postdoc Alpha and Herman. And before that, Zwicky was looking at clusters of galaxies and looking at how fast these galaxies were rotating in these clusters about each other. And from that, the assumption that Newtonian gravity was causing that motion, he could figure out how much mass he needed to produce the gravitational fields to give him the motions he saw. And he discovered he needed a lot more mass than he could see in the shiny parts of those galaxies, the stars, and the hot gas. And so he'd ended up discovering dark matter. So there has to be matter there to produce those gravitational fields that he needed to produce those motions. And the motions were pretty slow, so they were non-relativistic, maybe up to most a few thousand kilometers a second, and so that's called a non-relativistic. He didn't know this was non-baryonic. That came much later when this number got pinned down. And this work developed over maybe almost a half a century before people became convinced that there's dark matter that's not baryons out there. And more recently, people have found something even stranger, which is called dark energy. This is to distinguish it from matter. This is not energy in the sense of kinetic energy or chemical energy or any of those usual usages of that word. if this is made up of particles, those particles are going to be extremely light and they're going to be moving at speeds close to the speed of light. So this is going to be relativistic. This is non-relativistic. It's also non-baryonic, and it's the biggest contributor to the energy budget now. So that's what I want to focus on, this biggest contributor, which is the dark energy. And I'll look at a couple of other things also in this talk. So the first thing I'm going to use is the descriptions of a couple of models. There's the standard model where dark energy is a cosmological constant and you have cold dark matter. And then I'm going to make it dynamical by using a scalar field. And people don't use the scalar field model that much in analysis of data because it's complicated to use. So what they use are parameterizations, which are somewhat arbitrary. And some of you might be familiar with this parameterization, sometimes called WCDM or XCDM, where the dark energy is dynamical, but it's described in terms of a fluid. And now this two-parameter fluid dark energy parameterization has got more popular because of the DESI results. So I'll look at both of these parameterizations. And we're going to make predictions from these models, and we'll compare these predictions to observations, and then try to constrain those parameters, the models that are part of the predictions. And we'll look a little bit at various things that aren't related to those predictions, like, for instance, the transition from when dark matter dominates and you get decelerated cosmological expansion to the more current time when the acceleration is evident in the cosmological expansion and dark energy dominates. And then I'll talk a little bit about the value of the Hubble constant and measuring the curvature of space. That's mostly motivated by the fact that the Planck CMB results mildly favor very, very small curvature and its closed geometry. I'll also talk a little bit about the excess weak lensing in this Planck data, and then look a little bit at the DESI results. So we know Hubble's law, and that's in this form, the recession velocity of galaxies is proportional to their distance from us, with the constant of proportionality being the Hubble constant. And my favorite value is about 68. And this law holds at all times, except this constant depends on the redshift at which you're looking at this law. And when you're looking at that constant of proportionality is a function of redshift, it's called the Hubble parameter, and the current value of the Hubble parameter is the Hubble constant. So this is an illustration. It's a famous plot. It's from Wendy Friedman's group when she was leading one of the key projects on the Hubble Space Telescope. And this is the Hubble law then from 2001. So the recession velocity is on this axis, the distance is over here, and the numbers are down here. These are the residuals. And you can see which right straight line is a reasonable fit to the data. V is proportional to R. And the slope of this is the Hubble constant. In 2001, it was 72. And my favorite value is 68 plus or minus 2.8 or so, and maybe it's a little bit tighter than that now. And this number it was originally based on a method that we developed in 2001, the same year as this paper was written. And if we use median statistics to analyze compilations of Hubble constant measurements, the Hubble constant is the most measured parameter in science as far as I can tell. There's probably about 800 measurements of it now. And we went back in 2011 and looked at 553 measurements of them, of the Hubble constant, and used median statistics to get this. And these error bars include the error bars due to systematic errors, because you can do the analysis for many, many different Hubble constant techniques. And the scatter between those different techniques, the Hubble constants corresponding to those, give you the systematic errors. So it's pretty tight. And this is from a decade and a half ago, and this is my still favorite value. And there's a number of issues with the Hubble constant right now. This is one example. There are measurements that are based on Cepheids and type 1a supernovae that give you a slightly higher value. And so I want to compare these two values. And what I'm going to do is to look at data from large angular scales, the microwave background, small angular scales, the microwave background, and galaxy clustering data in the context of the ΛCDM model. With one extension, I'm going to allow the number of relativistic degrees of freedom to vary. And I'm going to marginalize over everything except the Hubble constant and n effective. And we know in the standard model of particle physics that there should only be 3 neutrino species. It's the way they decouple gives you something slightly higher than that. It's 3.046 or so. But you can see what the issue is here. If you use as a prior this number, then you get the red error bars, and you can see the red error bars are more than 2 sigma away from what the standard model wants. And it favors something like 4 like neutrino species or 4 relativistic species, while the blue numbers, the error bars are quite consistent with what the standard model predicts. So it's quite remarkable that in 2012 that the standard model of particle physics could distinguish between a Hubble constant of 68 and 74. If you go back a decade or a decade and a half earlier than that, you didn't know the Hubble constant to even a factor of 2 or so. It was somewhere between 50 and 100. So this is one way of explaining a larger Hubble constant. And it's also one way of saying that the standard model of particle physics favors a lower Hubble constant. But I'll come back to the Hubble constant in a while. So we know that the universe expands. And so we have preferred observers. Those are the observers that are at rest with respect to the expansion. And so it's really important to phrase everything in terms of these observers, these guys called cosmological observers, because these are the ones that see the isotropic expansion. And then you can generalize that isotropic expansion about us to saying that we're not preferred, and any observer anywhere should see isotropic expansion or isotropic matter distribution. And then you live in a homogeneous universe, and that's got much more symmetry. And if you ignore the possible global topologies you can have and just go with the simplest ones, you only have 3 options for the geometry of space. So I'm going to show you the 2-dimensional analogs because I can't draw the 3-dimensional ones. And for those of you who've done GR, this is the line element, and this is the spatial part of the scale factor here for these different spatial geometries. So you can have the flat geometry, and it's going to go out to infinity in good dimensions, and it corresponds to a critical energy density, and I'll introduce omega naught in a second. So that has 0 spatial curvature. Excuse me, that spatial curvature here. You could have the flat, the closed geometry, just the surface of a sphere, and as time goes on, it gets bigger and bigger. And that's overdense, and that has positive space curvature. Or you could have the open geometry, and that's a saddle, and it's going to go out to infinity in both dimensions, and that's got negative space curvature. So we need equations of motion, and we need a dynamical variable. And the simple way to think about it is to think about the closed geometry as it gets bigger and bigger. Very roughly, you can think of the dynamical variable as being proportional to the radius of the balloon, and that's the scale factor. And from Einstein's general relativity, you get the equations of motion for the scale factor. And this is for an ideal fluid model with ideal fluid matter. So you have a density and you have a pressure. The density, the mass density or the energy density is rho, and the pressure is P. So the Friedmann equation in this form gives you the expansion, the energy in the expansion is driven by the mass density, because that's the source of the gravitational field, as well as the curvature of space and a possible cosmological constant. And rho changes with time, so get that time dependence, you need to use energy conservation. And this is what you get. This is just PdV work as the expansion proceeds. And to complete this, you need an equation of state that gives you the pressure in terms of the energy density. So we know if things are redshifted, that things are moving away from us. And so A dot over A, so dot is the time derivative, and so this is the expansion rate. This is positive. And the next thing you might be interested in is the second time derivative of A, which you can easily get by differentiating these and doing a little bit of calculus. and you get this Friedman equation, the second time derivative one, that tells you. So if you ignore lambda for now, and the curvature does not show up in this equation, so you get matter, and this is cold dark matter and baryonic matter, and you can see there's a negative sign here. So this is telling you that if you have ordinary matter or even matter that's moving, so you have kinetic energy, so that's the energy of motion, and from E equal to mc squared, it gives you a mass, and you're looking at a mass per unit volume. So this contributes also. This is the active gravitational mass density. So it tells you there's going to be deceleration, that A double dot is negative. And if it turns out that you need accelerated expansion, you somehow either have to throw GR away and get rid of this equation, or if you want to keep this equation, you have to introduce a cosmological constant or dark energy with a strange equation of state where P is equal to minus the energy density. And then this term is negative, so it's minus 2 rho sub lambda. If rho sub lambda is significantly bigger than rho sub matter, this negative part will overwhelm this and make everything inside the square parentheses positive or negative, and that negative sign will cancel with that, and you get accelerated expansion. And this is why we introduced dark energy, because we know that A double dot is positive, and we want to keep Einstein's equations because we know that it works for black holes, for gravity waves, and we want to be a little bit conservative. And it would be a silly thing to do, except you have half a dozen ways of measuring the presence of dark energy, and they're all roughly mutually consistent. So it might not be that silly to introduce dark energy. So this omega introduced previously was the ratio in the energy density to this critical energy density, rho sub c, which is the energy density corresponding to the Einstein de Sitter model, where you don't have curvature and you don't have lambda. And so rho is completely determined in terms of the Hubble constant if you evaluate it at the present time. And this is what you get. So it's roughly 10 to the minus 29 grams per cubic centimeter. That's the scale. So dark energy, the way it was detected was to look at the expansion rate and how it varies with time. So we're going to compare cartoons of two different universes, one that expands slowly, the blue line, and one that expands more rapidly. And this is the Hubble law in both of them. And you can look at a galaxy at the same distance away from us in these two universes, and in the more rapidly expanding one, it's going to be moving faster, and the less rapidly expanding one, it's going to be moving slower. So as you go out in distance, you're also looking at earlier and earlier epochs of the universe, because it takes longer for that light to reach you. And so you have three options. It could be that the expansion rate was constant and you have the purple line, or it could be like in the past that it expanded more slowly, like the blue line, and that it's got to the present, it expanded more rapidly. Or it could be in the past that it expanded more rapidly, like the green line, that got to the present, it expanded more slowly. So this is a decelerating universe, it's an accelerating universe. And so what you want to do is measure this as far back in time as you can. And in the 1990s, the objects you could use for that were the type 1a supernovae. And they mostly ended up in the blue part of the diagram, giving you this line as a better fit. And you've probably all seen plots like this. This is an old one from almost 2 decades, more than 2 decades ago. The error bars have shrunk, the statistical error bars have shrunk, and the systematic ones have expanded. But overall, we see dark energy now at about 4.5 or 5 sigma. So this is omega lambda on this axis and omega matter. So this is ordinary matter and dark matter. And if you didn't have accelerated expansion or you didn't have dark energy, you should lie somewhere along this line, 0 omega lambda. The supernovae force you up here, and you can see at that point it's about 3 sigma away from 0. So that's telling you in the Friedman equation you have to have negative pressure to give you accelerated expansion. So we know there's dark energy there, and the best model right now that we have, and the simplest one, is the cosmological constant model. But that's very difficult to reconcile with most of the rest of particle physics. And so what we want to see is whether that's the best fit model or whether dark energy could be a function of space and time, and then maybe it becomes a dynamical field. And you could introduce one extra field in the standard model of particle physics to describe dark energy. So we're going to look at a bunch of different models. And in all cases, I'm going to assume that GR is correct and the astronomers have done all they need to do to check their results and they have all the systematic errors under control. So I'm going to look at a number of models and I'll start out with the standard model, the ΛCDM model, and I'm going to look at it at later time. So I'm going to ignore radiation. So there's no 1 over a to the fourth in here. So we have the Friedmann equation. You have ordinary matter and dark matter, and that drops like 1 over a cubed, and that's the blue line. So this is density against scale factor. We live over here, and the baby universe is over here, and it's a log-log plot. So this power law becomes a straight line and it's dropping with slope of -3. Space curvature drops with a slope of -2, and the cosmological constant doesn't vary with time. So at earlier times, you're dominated by dark matter and baryonic matter. At times close to the present of the cosmological constant dominates and you get decelerated expansion. You have, accelerated expansion and decelerated expansion back here. And it looks like there's 3 free parameters here, but there's only 2, and we'll see that in a second. So the conventional choice is to choose the density parameter of matter at the present time and the density parameter of the cosmological constant, which doesn't vary with time, so there's no 0 on it. The 0 says that's the present time. And you can immediately see the problem with the cosmological constant because this is an energy per unit volume. And if you rewrite this in natural units, it's the energy to the fourth power. And if you take the fourth root of that, that tells you the energy scale. And the corresponding energy scale is around a milli-electron volt. And until very recently, there was nothing fundamental in physics that's happening at that energy scale. It's sort of the energy scale for chemistry. And so that disturbed a lot of particle physicists that you're introducing this new substance and you're introducing it at an energy scale at which we thought we understood physics really well. And the last decade or so, people have been seeing neutrino masses somewhere around this energy scale. And maybe dark energy has something to do with neutrino masses, and there's been lots of papers written on that, but I haven't seen a very convincing model yet. So one way to get rid of this energy scale and make it much, much larger is to tilt this green line a little bit. And because the universe is so old, as you go back way in time, it'll correspond to a much higher fundamental energy scale. And as the time goes on, it drops down to a milli-electron volt. And you can do that with the fluid. So we'll go back here and I'll make it flat now. I'll come back and look at the non-flat geometries in a bit. But to make this simpler, I'm making this flat. And so we have ordinary matter and cold dark matter, which is the blue line again. And now we have a green line. And this is another energy density and another pressure. It's an X fluid or an omega fluid or a W fluid. And it's got an equation of state such that this equation of state parameter is negative and less than -1/3, and that gives you accelerated expansion. And so you have a downward sloping line. And because it's spatially flat, there's only 2 degrees of freedom here. And so omega matter now on W sub x is equation of state parameter. So this model doesn't make sense because you know to get the speed of sound squared, you just take dp d rho, and you do that with something with a negative sign out here. The speed of sound squared is negative, and so the speed of sound is imaginary, and you're going to get exponentially growing perturbations that drive you away from spatial homogeneity. And this doesn't look like the universe we live in at all. So what people do when they do analysis with this model is to arbitrarily set this parameter to unity, and it's not a physical model. So you can make this a physical model by using a scalar field with a potential energy density, And that'll give you an energy density that has the kinetic part of the scalar field energy. That dot is the time derivative. And I've chosen this particular inverse parallel potential energy density. And I'll come back to a second why I've chosen that form. But again, you get ordinary matter and dark matter, and that's the blue line. And then you get the contribution from the scalar field. And because this is a dynamical variable, you have to have the Klein-Gordon equation, phi double dot plus the Hubble drag plus the dv phi term. And this can't be solved analytically except in certain limits. And if you solve this numerically, you can also show this analytically that there's always attractor solutions for this potential energy density form. And the attractor is such that when the scalar field energy density is subdominant, it wants to come to dominate over the dominant energy density. And that might be a really useful thing because it wants to come to dominate. And so it can tell us that it's going to take over eventually. And maybe that explains why we have dark energy now. But it's not a straight line, and it's a sloping line, and that depends on what kind of dominant dark energy you have. And the parameters for this model are omega matter now and alpha, this index up here. So we're going to take predictions and compare these predictions with some older data because the error bars were much larger then, and it's easier to show other plots with these larger error bars. So I look at Type 1a supernovae, apparent magnitude versus redshift data, and then baryon acoustic oscillation data, Hubble parameter as a function of redshift, and growth factor as a function of redshift. And to illustrate the procedure, I'll show you this in the ΛCDM model, where instead of working with scale factors, we work with redshift, which is 1 plus z is equal to scale factor now divided by the scale factor at the earlier time you're interested in. And you can re-express the Friedmann equation in this form. So you have omega matter, omega curvature, and omega lambda. And if you evaluate this, the present epoch, this becomes h naught squared, and these two guys cancel, and that becomes 1, that becomes 1. And you get the sum rule. So even though it appears we have three free parameters, there's only two because the sum rule has to be satisfied. And so the conventional choice in this case is omega matter now and omega lambda. And then you can make a prediction for the Hubble parameter through this equation that depends on the redshift you're looking at and on the cosmological parameters and on the Hubble constant because it shows up over here. And it's Hubble constant times the square root of the guys to the square parentheses. And so you make predictions and then you compare to the observations you have at various redshifts, whatever technique you want to use. And I'll show you results, and I'm going to show you parameter plots like this. So there's always going to be three plots, lambda CDM over here, x CDM over here, phi CDM over here. On this axis, it's always omega matter now. On this axis, it's the other parameter. It's omega lambda for lambda CDM, w sub x for x CDM. It's the equation of state parameter, and at w sub x equal to -1, you get lambda back, and that's the flat lambda CDM model on this plot. And on this plot, it's going to be the parameter alpha, so it's phi to the minus alpha, which is the potential energy density. And at alpha equal to 0, you get back flat lambda CDM. And on this plot, flat lambda CDM is this line over here. Closed geometries are up here, open geometries are down here. Both of these are flat geometries only, and we'll go back and put in curvature later. So you can see a bunch of lines here. So these dotted lines divide you between currently accelerated expansion and currently decelerated expansion, and the same here, and the same here, and the same here, and the same here. And these lines, the dashed lines, are all flat lambda CDM. So a model with omega matter of 0.3 here is identical to a model with omega matter of 0.3 here, and it's identical to a model with omega matter of 0.3 here. So these are older type 1a supernovae data, and you can see the three contours, the 1 sigma, 2 sigma, 3 sigma contours, 1 sigma, 2 sigma, 3 sigma, and the best fits over here. So the first thing we can see is that it doesn't matter what model you use to analyze these data. they always almost entirely favor the accelerated expansion part of parameter space. So that's a useful test. The other thing you see is that the standard model, which is omega matter of zero point 0.3 or so, omega lambda of zero point 0.7, and flat geometry, is right near the best fit point, and it doesn't matter which model you use to analyze the data. And the contours are pretty broad. So they allow space curvature, they allow space curvature, sorry, they allow dark energy dynamics and dark energy dynamics. So the standard model is very good fit, and you get accelerated expansion. And if we look at baryon acoustic oscillations, you have similar sort of contours. But the important thing is that the contours now have a different principal axis. You compare them, so they're almost orthogonal. And so you can see that when you start combining data and use baryon acoustic oscillations at supernovae, you'll get a much smaller part of the allowed parameter space. But again, the standard model is a good fit to these data. You get accelerated expansion in most of the parameter space. And there's lots of room for space curvature, lots of room for dark energy dynamics. And you can see that with Hubble parameter measurements. But since we're using the Hubble constant as one of the Hubble parameter values, there's two different values of it, 68 and 74. And you can see that there's two sets of contours. They move by half a sigma, but they're both consistent with the standard model, and they're both consistent with the accelerated expansion. And so you have this extra systematic effect, and you're allowed space curvature, you're allowed dark energy dynamics. The data don't rule those out yet. And this is from growth rate as a function of redshift. So the standard model fits these data very, very well with omega matter of zero point 0.3 and omega lambda of zero point 0.7, but there's lots of room for spatial geometry, non-zero space curvature, lots of room for dark energy dynamics. So you do the obvious thing and look at two data sets at a time jointly, and you get much smaller parts of parameter space that are allowed, and the standard model fits really well. And there's room for less room for spatial curvature, less room for dark energy dynamics, but they're still allowed. And it doesn't matter what data sets you look at. So this again is Hubble parameter data, and there's two Hubble constants, so they move by half a sigma. So I can go through this relatively fast. It doesn't matter. But two data sets at a time are consistent with the standard model with omega matter of zero point 0.3, omega lambda of zero point 0.7, but they don't rule out some dark energy dynamics or spatial curvature. And we see interesting things. So you can look at this in more detail. So different supernovae compilations move the constraints by half a sigma. So if you look at, we already saw that with the Hubble constant. And the same thing's true with omega baryons times h squared. So that you, depending on where you get omega baryons from, whether you get it from lithium or you get it from deuterium, you move the contours a bit. And you can do this with other data sets. So there's systematic effects, and we'll come back and look at the best data that we have currently and look at the conclusions then. So I want to change gears a little bit and look at this transition from dark matter dominated decelerated expansion to dark energy dominated accelerated expansion. So I'm going to plot h, the Hubble parameter divided by 1 plus the redshift, because that allows us to show this on a linear graph here, because if you do include that, this goes up really, really sharply, and it doesn't, it's not so obvious to see this change. So it's a function of redshift. This is higher redshift, about 2.3 is the highest data when we looked at this a decade ago. And there's 6 models here that best fit these data because they come in pairs with two different values for the Hubble constant, 168 and 174. And these are 3 sigma deviant models. So you can see the best fit models have a dip in them. And it becomes a little bit clearer if we start binning these low redshift data in redshift bins. We can't do that at high redshift because the data is too sparse. But if we do that, you can see in the bins with 2 sigma error bars that it favors an expansion rate that decelerates initially and then starts accelerating. And if you interpret this in terms of the lambda CDM model, at higher redshift, this is the dominant term. And so the slope is going that way. At lower redshift, this is the dominant term, and the slope is going that way. And you see this deceleration, acceleration transition. And the redshift then was about 0.74. It's roughly that now. The error bars have increased a little bit because more systematic errors have been included. So the next thing I want to do is look at measuring the Hubble constant in another way that's independent of the CMB and it's independent of local calibrators. So this is another low redshift measurement. So what I'm going to do is I'm going to look at a lot of low redshift data, but not use the CMB data. So I'm going to look at baryon acoustic oscillation data that go up to redshift of 2.3, Hubble parameter data that go up to redshift of 2, supernova Pantheon plus compilation that goes to redshift of 2.3, quasar angular size data that goes to redshift of 2.7, reverberation mapped MG2 data that goes to redshift of 1.9 and C4 data that goes to a redshift of about 3.4 and Abati correlated gamma ray burst data that goes to a redshift of about 8.2. So almost all the statistical weight is in these three guys. These guys just tighten things up a little bit. And we've looked through these individually and seen that the constraints are consistent, they're mutually consistent. That's why we can jointly analyze these. We've also discarded a number of data sets, and I'll talk about that a little bit later, whose constraints are not consistent with the rest of these constraints. So I'm going to not use local calibrators. I'm also not going to use the CMB. And what I'm going to do is I'm going to use omega baryons and omega cold dark matter as the free parameters, and instead of just omega non-relativistic matter. And if you do that, you can compute in each of these models the sound horizon at the drag epoch. And so that's the way we calibrate the BAO data. We're not using Big Bang nucleosynthesis. We're not using CMB. We're not using local calibrators. And we can fit this with a whole bunch of different models. And if we do that and marginalize over all the other parameters in these models and just get the likelihood of the Hubble constant, you can see that they're all completely consistent with each other. The error bars, the statistical ones are plus or minus 2.4, and the systematic error bars, this is the lowest value, that's the highest value. They differ by 0.6. So you can half that and call systematic errors plus minus 0.3 and add that in quadrature and then take the arithmetic mean of these guys. And that gives you a Hubble constant at lower redshift that's about 69 and a quarter plus or minus 2.4. And that's very consistent with the median statistics value. It's also consistent with Friedman's group estimate of the Hubble constant in this paper. It's been published. I haven't updated, but it got published this year. So what they're using is Webb telescope and Hubble telescope, tip of the red giant branch as local calibrators to calibrate supernovae and then get the Hubble constant from that. And it's not that consistent. It's about a sigma and a half smaller than what Adam Rees's group gets using Cepheids as local calibrators for the supernovae. And that there is a Hubble tension. And the first part of it is that these local calibrators differ a bit. And it would be really useful to understand why they differ before comparing just the Cepheids to the CMB. So that's a really interesting thing to try to resolve first before focusing on the difference between this number and this number. And other CMD experiments are quite consistent with the Planck estimates. They're also consistent with the median statistics. They're also consistent with the model fits to low redshift data and the tip of the red giant branch calibrators. So there's some really interesting stuff going on, and I think once we resolve this, then we'll know whether there's a inconsistency between high redshift measurements of the Hubble constant and low redshift ones. So we can look at other issues. The Planck data favors at weak significance closed geometry, but they mostly looked at ΛCDM models when they vary domain curvature. And it's possible that you get better and more interesting results on spatial curvature if you consider dark energy, dynamical dark energy models like XCDM and the PhiCDM. And then maybe you don't get such tight constraints on spatial curvature. So I want to look at dynamical dark energy models with have non-flat geometries. So we'll start out with this guy, XCDM, and put back space curvature, and that's the orange line. And now you have three parameters. There's this guy also, plus the two guys we start with. And I'll do the same thing with PhiCDM. I'll put back space curvature, which is the orange line. We have three free parameters, omega matter, omega curvature, and alpha. And I'm not going to show you the triangle plots because they're pretty messy, but I'll show you results, the results of spatial geometry from these guys from the same data set I showed you for the Hubble constant. And I'll elaborate a little bit on the other data sets that we looked at and discarded and did not use. One was the X-ray UV correlation of quasars, and some of you might be aware of Lusso and Risolati's papers on this. So we showed that these guys are not standard candles, so you can't use them for cosmology or pretty much anything else. We also looked at reverberation measured H beta quasars and showed that they're not standard candles. And people have tried to use starburst galaxies as standard candles, but we showed that there's evolution in this data set and you can't use them as standard candles. So these are three of the data sets that we didn't use. But using all these guys, you can see that spatial curvature is consistent with zero, at the most deviating by about a little more than 1 sigma. But dark energy, the dynamics is more deviant and it's away from a cosmological constant by almost 2 sigma in most of the models we looked at. So we can't really say anything. 2 sigma is not strong enough, but it's worth looking at more carefully. And I want to take a little bit of a detour and look at these reverberation measured mapped quasars as standard candles. So this is the model we have. There's a massive black hole here, an accretion disk in a torus, and you can measure luminosity of this, the apparent luminosity, and the apparent luminosity of the stuff that comes out here through the line emission. And the assumption is that the black hole is radiating stuff out that excites this and causes these emissions. And it turns out there's a correlation between the time lag from the spiky, whatever you see from the radiation from here and the later radiation from here, that's correlated with the absolute luminosity of the source. And you can see an example here of the time delay versus luminosity for this is for C4 and for some of the MG2s also. And this is the best fit radius luminosity line. So we've typically had 50 to 100 quasar compilations so far, and there's a strong correlation, but the data is not restrictive enough to give you good cosmological parameter values. But with Rubin turning on, we should get 10 to the 4 or 10 to the 5 such quasars that go all the way to a redshift of 4 or so. And so this is one way of filling in the gap because supernovae and BAO are not really going to go much above 2.5. And it's useful to get higher redshift data where you can probe things that are at redshifts higher than 2.5. So the next thing I want to look at is non-flat geometries of the CMB. And so we'll put back this model. We have spatial curvature over here. And unlike the flat case, now we have two length scales. We have the Hubble length and we have the curvature length. And so you can't use the standard Hubble, the Harrison-Peebles use, all of which follow past spectrum for fluctuations. But you've got to actually compute in open and closed inflation models what past spectrum you can use. And Planck did not verify that the past spectrum they assumed when they were analyzing for spatial geometry comes from an inflation model. But we've got some work that we're just finishing up showing that it's a reasonable assumption to use what Planck used. So in the spatially flat case, because there's only one length scale, it's reasonable to assume a k to the n past spectrum because the scale is set by the Hubble constant or the Hubble parameter at that epoch, and that shows up in the denominator, and that gives you something dimensionless. But if you have a closed model, the modes are discrete, and this is the eigenvalue of the spatial Laplacian, where A is integer valued, and it starts at 2 and goes all the way to infinity. And this other parameter that's usually used is Q, which is A plus 1, and this length scale, the curvature scale that has to be introduced. And the open model is somewhat similar, except you have a continuous spectrum for the spatial Laplacian, but the spatial harmonics are different than for the closed, for the flat case. So initially in the 1990s, people were interested in open models because we knew that omega matter was much less than one, and spatial curvature could have given you the rest of the stuff that fills that into unity. And we were looking at slow roll inflation models, and we could derive exactly in non-flat models the past spectrum. And this is known to be inconsistent with the Planck data because there's no tilt here, even though there's some structure at very, very large angular scales. But when you go to answer 50 and 100, you can look at the CMB and you know it has to have some tilt. And so this doesn't fit that well because at L's of 100 or so, this reduces to this far spectrum. And it gives you k to the 1, actually, not k to the n. So more recently, Planck have taken this and multiplied by k to the n minus 1 and used that in the analysis, but they didn't justify multiplying by k to the n minus 1. And so what I've looked at is far spectra for more complicated inflation potential energy densities that depend on the inflaton through cinches and gauches of the inflaton. And the analytic expressions are really messy, but we can see the power spectra over here. So if you look at the open case, this is the matter, primordial matter power spectrum. In the flat model, it's the blue line. In the model that Planck used in the analysis, it's the black dotted line. And in the model that I computed in this inflation model, it's the red line. But these are at very, very large angular scales. And so there's going to be cosmic variance. And even though there looks to be huge differences here, those differences are not that important. And what's playing a more important role is what's going on over here. And so I'm going to analyze these, and it's really messy because the data I'm using and the number of models, and I'll try to make sense of this. So I'm not going to use DESI data. I'm going to use Planck data from the 2020 ANA paper, TTTEE plus low E. And I'll also use the lensing potential power spectrum data, that's called lensing, and non-CMB data, which is BAO. There's 16 of them, including 4 growth rate measurements, then 9 independent growth rate measurements that come from velocity measurements, then 1590 Pantheon plus supernovae measurements, and 32 Hubble parameter measurements. And I'm going to constrain 12 different models. There's going to be 6 lambda CDM models, 6x CDM models. So they're pairs of 3 different types of models: the flat tilted model with the k to the n power spectrum, the non-flat tilted model with the power spectrum assumed in the Planck papers, and the non-flat tilted model with this new power spectrum. So that's 3. And it's going to be width out and width this parameter capital A sub L. So this is a phenomenological parameter where you reintroduce the lensing potential power spectrum or the 2-point function and parameterize it with this. And you expect at the end of the analysis to get back A sub L equal to 1 if your best fit model gives you the right amount of gravitational lensing. And it turns out that you get a deviation of about 2 or 2.5 sigma with A sub L greater than 1. And that's suggesting that the Planck C sub L's over a certain range, I mean, they do appear to be smoother than you would get in the best fit ΛCDM model. And there seems to be something strange going on with the Planck data. And we've got to do this because there's degeneracy with omega curvature, and we want to measure omega curvature. So I'll start out with the results. And so we're going to look at first with ΛCDM and first with A sub L equal to 1. And so there's 3 models we're looking at. And the first thing we're going to do is we're going to look at whether the constraints from the Planck data are consistent with the constraints from the CMB data. And we're using a couple of different techniques. So one's called the suspiciousness, which can be related to something that's being used in weak gravitational lensing also. And you can look at these papers, and if you want, I can leave this up a little bit, or you can find some of these slides on the web also. So when you look at Planck data versus the non-CMB data, then the problem for ΛCDM is only 1.2 sigma when it's flat. And for the non-flat case, it's a little bit more than 2.5 sigma, a little bit less than 2.5 sigma. So I'm not going to throw away data unless there's a 3 sigma deviation. So I don't claim that there's a significant inconsistency between P18 data and non-CMB data. So if you add in the lensing data and look at P18 plus lensing versus non-CMB, there's less of an inconsistency. And so we can jointly analyze these data together and then measure omega curvature. And if we do that, we see very, very tight constraints on omega curvature consistent with flat geometry. So there's no indication here that you have non-flat geometry as was claimed earlier in this paper, Di Valentino, Melchiori, and Silk. When you combine CMB data with non-CMB data. So if we go and see what happens when we also allow A sub L to vary, the inconsistency decreases, and you can go ahead and combine all these data again and marginalize over everything else and get omega curvature, and it's consistent with flat geometry. But if you just look at A sub L deviates by about 2.5 sigma from 1. So this PR3 data release, which is the Planck 2018 data, seems to want more lensing than is predicted by the standard ΛCDM model. But interestingly, both the other CMB experiments, they have bigger error bars, and they don't deviate from A sub L equal to 1. So it might be something just to do with the Planck PR3 data. We can look at, ΛCDM. And if we start out with A sub L fixed, then we see huge deviations between P18 and non-CMB and P18 plus lensing versus non-CMB. And so what's happening is that the CMB data wants phantom dark energy dynamics. So it wants an omega x that's less than -1, while the non-CMB data wants quintessence dark energy dynamics. So it wants the omega sub x greater than -1. And so they just, the constraints don't overlap. And so you can rule out this model. It just doesn't fit the data. If you assume CMB data and non-CMB data correct, the model's ruled out. If you allow A sub L to float and be determined from these data, then the deviations between them shrink to below 3 sigma. And then if we go ahead and combine all the data and just try to measure omega curvature, there's about a point, three-quarter sigma deviation away from flat geometry. But interestingly, it's deviating towards the open side. And if we leave omega sub x, so omega is the only free parameter, you get about a 1.5 sigma deviation from cosmological constant favoring dynamical dark energy. But again, this is not very significant. But in both cases, A sub L deviates by more than 2.5 sigma from 1. So again, there's a problem with the sweep cleansing issue. And this might not be the case in the PR4 data release. But before I get to that, I want to go, how much time do I have?
10 minutes.
Okay, great. Look at results from, this is not using the DESI data, this is using our data, but we're going to analyze this omega naught, omega A CDM model. And this is a model where the equation of state parameter is of this form. And it's really interesting here because if you go to zero redshift, it gets down to this constant, so it becomes the XCDM model where that's the equation state parameter. And if you go to very high redshift, this becomes unity, and then you get this equation of state parameter. So this model is two XCDM models, one at low redshift and one at high redshift. And the CMB data is going to constrain that more than it constrains this, and the non-CMB data is going to constrain this more than it constrains that. And you can see what happens here. So we can go over, so lambda CDM is omega naught equal to -1, omega A equal to 0. And if you just focus on this panel over here, this is omega A, this is omega naught, and lambda CDM is where those two lines intersect. And the gray contours come from non-CMB data, and they favor quintessence dark energy dynamics, while the red contours come from the Planck data, and they favor phantom dark energy dynamics. And these two guys, they deviate by 2.2, 2.3 sigma, so they don't deviate by 3 sigma. So we can jointly analyze them, and then you get the blue contours. And these blue contours give me these numbers. So if you focus on omega naught, it's minus 0.850 plus or minus 0.059. This is the DESI first year results. So from our data set, we get slightly tighter constraints than DESI, including the constraints in omega sub A, and they're tighter than DESI's. But the point is that at lower redshift, omega naught is consistent with quintessence. It's less than, it's great, more positive than -1. And at higher redshift, it's consistent with phantom. And the two interesting things from this is that the DESI results hold even if you do not use the DESI data, so it doesn't have anything to do with the DESI data. And we also redid the analysis without using any of the supernovae data. And you get a 2 sigma support for dark energy dynamics, so it doesn't depend on the supernovae data. So it doesn't depend on DESI, it doesn't depend on supernovae. And we can look at what happens when we allow A sub L to vary over here and look at a more complicated model. And you cannot see the non-CMB gray contours unless you look really, really carefully. They're hidden over here. And the CMB contours have shifted, so they're not that far away from lambda CDM. And they're well consistent, the non-CMB and the CMB, and you get a 2 sigma blue contours here that are joined. And it's just barely 1 sigma away from lambda CDM. So instead of being 2.2 sigma away from lambda CDM, it's now 1.35 sigma away from lambda CDM. But A sub L now deviates by 2 sigma from lambda, from what you want if your gravitational lensing stuff is correct. So again, I don't know if what DESI is seeing is just partially caused by this excess gravitational lensing smoothing of the Planck data. And So neither of these are not physical models, and we've looked at ΛCDM model, but that was with the 2015 CMB bank data, and we're getting slightly better fits with the ΛCDM model than with ΛCDM. But we're trying to finish up a 2018 bank data analysis of this, and we'll know better results maybe in a couple of months. So the Planck PR4 data has less support for Isabel deviating from -1. And so we're looking at that analysis of omega naught, omega ACDM also, and we should have results in a couple of months also. So I'm just going to go over open questions here. We don't know what the dark energy is. The universe is probably not closed, it's probably flat. And for theory, it's really interesting to try to understand these non-flat inflation models because they're pretty interesting physically. So we don't know whether this evidence for Isabel is a problem for the ΛCDM model or whether it's a problem with the Planck data. And maybe with the analysis from the PR4 data, it'll become clearer. And we don't know what the dark matter is. So current data cannot rule out dynamical dark energy as long as it's not very rapid. And we should get some really good ideas from DESI and Euclid data about PAO and dark energy dynamics. And hopefully we'll learn something about dark matter from experiments at CERN and these deep underground experiments. And maybe these things will be resolved in a decade or so. But cosmology is not going to be over even if those are resolved. So I'll leave this up here if you're interested in problems to work on. And I can put it back later. Thank you very much.
Some questions? So if you have a space-time dependent data, then the rocket potential scale is new.
Yeah.
So lots of them, long continues to select.
Yeah. So it cannot, the scalar cannot couple directly to, it's only indirectly coupling to things. Otherwise, it's going to cause you problems with your force flow for gravity. And that's kind of unclear why it should be so weakly coupled, but it's got to be weakly coupled.
Yes. You said that standard motion can persuade like Hubble constant.
Yeah.
So just that number continues. You're talking about a and that is number continues, right?
Yeah.
So what if the number changes?
Um,
How would that be?
yeah, if the number changes, but it's I mean, so it gets really difficult to change the number of neutrino species because it's going to affect the width of the Z0 boson, the decay. And so the way you do this is you say the sterile neutrinos, and that seems to be somewhat contrived to do that. But the number of light neutrino species, I think, in the simplest version of the standard model is going to be 3, no matter what you do. And so if you want to use that as extra relativistic degrees of freedom to change the expansion rate of the universe to get you a slightly different Hubble constant now, then it's probably not going to come that easily from neutrino species. But it's just really remarkable that 10, 15 years ago, that just from the standard model of particle physics, you could distinguish between the Hubble constant of 74 and 68 if you allow the number of neutrino species to vary. It's 3, but because of the way they decouple, it's 3.046 or 3.045. And you can, there's lots of papers on this. Just go look at neutrinos in cosmology or review articles, or even the Planck paper, and then you can follow up from there as they try to measure an effective Planck data.
I have a related question. So, the varying ineffective have an implication for the case of L being bigger than 1. In terms of the damping CMB.
Yeah, I haven't seen too much work on that, but it might be an interesting thing to think about, to look at.
So, the CMB analysis you are showing for different kind of models, do they affect the reionization optical depth? I mean, of your
A little bit, but not a lot in these models. And because we're using a lot of other data, and so tau doesn't change by a huge amount, but it changes by a little bit.
on the real side? Or?
So I don't remember off the top of my head, but I have the papers here. I can look at it if you want to look at it. It's nice to see you again.
Yes, good.
I have many question. Like when we talk about the Hubble, I think the Hubble constant is h equals to 0.7 minus but why do we consider it such more?
Why do we need to get tighter constraints? Because if you want to measure the other parameters, it's going to affect them also. So it's one of the free parameters when you're fitting lambda CDM to data. And in the simplest version of lambda CDM, there's 6 free parameters. So if you can constrain the Hubble constant and replace that by its likelihood by a delta function or something close to a delta function, then you tighten up constraints on the other parameters, which you can't get through any other way. So you want to try to tighten each of these parameters as much as possible, even with the matter density. If you can use different techniques to measure omega matter, it'll tighten up constraints on the other parameters.
It's on your slide 24, I think. So when you were plotting the solid and dashed contours, it sort of looked like, I mean, of course, it's all within yeah.
Yeah.
So you have one before. Uh, off. So here, this is supernova data, right?
This is just Hubble parameter. Expansion rate is a function of redshift. It's not the supernova data.
Okay. Because what is I mean, the straight one, which has 67, it's much more preferred than the dotted one. So I was wondering, like,
I mean, it is not much preferred, right? It's about half a sigma, right?
but at least visually it gives you the indication of the global who's slightly preferred to but
Yeah. So it is because I mean for lambda CDM, if you fit it to, I mean I don't know why it shows up preferred here, but it is preferred if you use Planck data and this other data.
it's true.
Yeah.
But this is not like with CMB, right? It's the lower redshift.
Yeah, this is low redshift.
And still this is preferred one, like that's why I got
Yeah. So yeah, the better thing to look for, well, that's really old data, but this is all low redshift data. It's all about it's somewhere around 69.
can I ask you a related question on this side? See, the thing is, it's like everything is consistent to the plant result for that C5 plus super. C4 has like one thing you would change to make everything consistent. That's the calibration of super like plus.
It's there seems to be. I mean, there's lots of low redshift measurements through calibrators, and maybe about 75% of them are more consistent with this or this number than they are with this. And so there especially seem to be issues with the Cepheids, and it's not clear what's happening. Maybe they just have much better data, and so they've got the most accurate number, and the other ones are wrong. But if you have to use astrophysical stuff, it seems really difficult to get error bars that are this tight. And there's an extremely long discussion in this paper about all the possible statistical and systematic errors, and it's well worth reading that paper in detail. So they go into all the issues with Cepheids and other local calibrators. So one thing is that you mostly see Cepheids near the centers of galaxies, while tip of the red giant branch you can see much further out. And so there's some issue of whether there's some kind of crowding, and so you can't get the Cepheids that cleanly because they're in crowded regions of the galaxy.
question there.
So in starting, you said that we are looking that the GR is that. Is there any other group for dark matter and dark energy other than just its mass or the presence of it? Like, how do we know that the theory of gravity is right? And
Okay, so we can start with that first question. How do we know the theory of gravity is right? So we know on small scales that it describes binary pulsars and binary black holes and gravitational radiation, right? And it describes that very, very accurately. It also describes the propagation of gravity waves over fairly large distances. And it's not that inconsistent with the CMB measurements if you assume that there's some dark matter and dark energy there. And the physics seems pretty clear that you get these oscillations and stuff. So it seems that the place that it's really breaking down is somewhere around 100 megaparsecs or so if you're interested in dark energy. And if you want to explain it, if you want to explain dark matter using breakdown of GR, that so far has proved pretty much impossible. So no matter what people have done, so even if you do things like MOND, so you can explain spiral galaxy rotation curves, but you've got to choose a special critical acceleration that's true, that's different from galaxy to galaxy. And then you're saying F equal to ma depends on which galaxy you live in, and that's a little bit disturbing. But the other problem with MOND is that when you go and try to fit clusters, you can't fit it with MOND without introducing more dark matter. And so MOND doesn't get rid of dark matter, and that's the closest thing that comes to getting rid of dark matter in galaxy scales. So I'm not aware of any modified gravity model that gets rid of dark matter. And if you want to get rid of gravity, GR, then you have to introduce many, many, many different couplings because your symmetries go away. And it seems very contrived to pick one or two different modifications and use that to fit the data and say that everything else is not modified. I mean, we have this problem even in non-Lorentzian invariant theories in particle physics. So once you give up on Lorentz invariance, I think you introduce like 30 or 40 extra parameters, and there's nice review articles I've forgotten his name. I think it's Kosztolewski in Indiana and reviews of modern physics, trying to constrain all these parameters. And I mean, if you want to introduce 40 or 50 parameters in place of general relativity, you can fit anything. And it seems to be better to be more conservative and go with gravity because it has worked everywhere else. And it's not just supernovae that are giving you dark energy, but baryon acoustic oscillations give you dark energy. CMB gives you dark energy. Hubble parameter measurements give you dark energy. And so if it was just one measurement and you're introducing a whole new hypothetical substance to explain that to preserve GR, that wouldn't be that reasonable thing to do. But I think the way you're going to make more progress is try to see if you can preserve GR and find a better dark energy model that's consistent with everything. But it's kind of a philosophical issue.
So there are strong benefits from the strong reduction lensing from the tiny days of lens changes. So I was wondering why they're not considered here.
For the Hubble constant. So they are consistent with the lower measurements when you put in structure, model the inhomogeneity of the intervening lens. And I haven't put that down, but there's many, many more measurements of the Hubble constant. I think there's like 800 measurements of the Hubble constant. If I listed every one, I still wouldn't get through all of them in an hour.
There was something on the chat. Let's check the question.
It's an interesting question. Shayantan, can you unmute yourself?
Hello, sir. Can you hear me?
Yes, please go ahead.
So I just had a very small question, not directly regarding. So I was wondering if you can comment about your work with Professor Peeble and Valenkin about the whether the inflationary field can be used as a quintessence field or not. I guess you have some work along with Professor Peeble and Valenkin that the scalar field, which is a residue from the inflation, could indeed be used as a quintessence. I mean, under some Traker solution, etc. So if you can comment on that, like the quintessence scalar field can be interpreted from the residue of the inflationary field or not. Thank you, sir.
Yeah. So in our 1988 papers, we tried to just connect this quintessence field to the inflaton, but we found that you had to drop the energy density quite a bit from when inflation ended to when this quintessence part took over. So it wasn't a very convincing model for inflation and quintessence. And in his paper with Vilenkin, they tried to build a better model. And there are models now where it can be a joint one scalar field to describe both the inflaton and the and quintessence. And I haven't really followed that in much detail, so I can't really tell you whether they're very convincing models or not. But it's a huge field for people to study now, and you could probably find lots of papers on that area.
Thank you very much, sir. Thank you.
Thank you.
Okay, so let's thank Professor Ratra again for an engaging